Hello, friends. This is AI A to Z. I'm Dr. Sonali Tamankar. Today we have AI for the Sleuth, or XAI, which I swear is a standard acronym for Explainable AI. I didn't make it up just to have a topic starting with an X. So, a lot of AI models are black boxes. Explainable AI, roughly speaking, attempts to understand the why behind an AI model's predictions. We briefly talked about a dogs versus wolves classifier in our B's for bias video, but today we'll get into more details. In a well-known explainability paper, researchers intentionally trained a flawed model about to classify huskies versus wolves. So in the training data for the model, all wolf images had snow in the background, while the pictures of huskies did not. So the model relied on a shortcut. Snow in the background means wolf. It really was a bad classifier. Then they took 10 new images of huskies and wolves. One husky was against a snowy background and one wolf was not. The model classified these two images wrong, but correctly classified the other eight. So it had an 80% accuracy. Now, 80% doesn't sound too bad, right? So when they asked 27 graduate students, 10 of them trusted the model to work well in the real world. Only 12 out of 27 identified the snow as a potential feature the model might have used. In a remarkable demonstration of the power of explainable AI, after the students were shown an image like this one, highlighting which portions of the image the model was using to classify, the trust in the model eroded. And most of the students were able to identify snow as a feature. So AI models will solve the problems we ask them to solve, not necessarily the ones that we want them to solve. In this case, we had asked the AI, here are some pictures of huskies and wolves. Learn everything you can from these images so that if I showed you a new image, you should be able to tell me if it's a husky or a wolf. Based on the images it saw, the model was entirely justified in classifying as it did. But this is definitely not what we really wanted or would have wanted in the real world. So, explainable AI helps us see what AI models are really focusing on when they make their predictions and lets us check whether that matches with what we think the model should be paying attention to. So, in a world where AI models are used to decide who gets a loan, who gets bail, who gets hired, explainability is critical. Now, some AI models are inherently interpretable. Decision trees work by following branches. So, for example, to predict home values, we might follow through the branches. More than 2 bedrooms, yes and no. Built after 2015, yes or no, and so on. The projected home value is some sort of an average of the other homes that meet the criteria. Linear and logistic regression are also inherently interpretable. So these can be thought of as glass box models. We can see inside. We often pay a price for the interpretability. The glass box models may not be as accurate as the black box models. The deep learning models used for complex problems are all black box models. Also, sometimes we may use methods like random forest, which average predictions from many decision trees. So these models are robust and accurate, more accurate than a single decision tree. But we lose interpretability when we use such ensemble methods. So now a method like Shapley values or line is then used for explainability when we have a black box model. Shapley values lets us ask, according to the model, what features pushed this particular prediction up or down. So if a model predicts a home price is 700K, whereas the average prediction is 500K, Shapley values will distribute the 200K difference across features. For example, some attributed to the zip code or the location, some to the bedrooms, some to the yard size, and so on. So, in the healthcare context, we can have two patients who are both equally at high risk of being seen in the emergency room, but maybe one is at high risk because of their clinical features. Maybe they have diabetes and hypertension, whereas the other patient is at high risk because they don't have insurance or don't have a PCP and they're only getting their care in the emergency room. So the overall risk scores don't give us the full picture. Techniques like Shapley values will help surface which factors the model is relying on for each individual patient, making it easier to follow up in a tailored fashion and support the patients in the appropriate way. So now coming back to the Huskies versus Wolves example, in the Why Should I Trust You paper, the technique that the authors demonstrate is called LIME. It approximates a complex black box model locally with simple interpretable surrogate model and then studies how much the output is affected when the input is perturbed systematically. So this is a type of model agnostic explainer. It can be applied in many different models, even when the model itself is black box. In the Huskies versus Wolves example, the explanation showed that changing the superpixels corresponding to the animal had little effect on the output, but changing the snow related background regions actually had a much bigger impact. So once we uncover that the model is relying on unintended background features, we can use this insight to guide model improvement. For example, by augmenting the training data with examples of huskies or with snowy background to reduce reliance on the spurious correlations. So in addition to the model agnostic methods, there are also algorithm specific methods like a tree explainer. Sometimes we want to understand feature importance in general for the whole model. So that will allow us to make statements like chronic heart conditions are one of the most important predictors of emergency room visits. On the other hand, sometimes we want to understand features that drive one specific prediction. Why is this particular patient at high risk? Or why was this particular applicant denied a loan? So there are many explainable AI models designed for these different goals. We are not going to attempt a full survey here or get into fine distinctions like interpretable versus explainable versus trustworthy AI. Instead, I've linked references below, including a comprehensive guide that runs 250 pages. So, moving on, let's ask what are the different motivations for XAI? So, mitigating bias and working towards fairness is one reason for using explainable AI methods. In some domains and some geographical areas, there may be regulatory requirements like right to explanation. In a field like healthcare, earning provider trust and confidence requires explainability. And without trust, AI implementations will run into adoption friction. Understanding individual patient risk factors might make the findings more actionable. And explainable AI also allows for accountability, ensuring that systems can be audited and held responsible. Explainable AI may also have a technical goal. It can help with debugging and model improvement. The ability to explain prediction can in itself be of value in communication and storytelling. So, everything we have discussed so far mostly comes from traditional machine learning, though interestingly, some methods like Shapley values can generalize. Now, with large language models, things get even stranger. Explainability sounds easy in this case. Since the models are so good at language, let's just ask the model to explain itself, for example, through chain of thought. But here is the problem. The explanation is also generated text. Recent research shows that models can produce explanations that look sensible because they know they are being watched, not because that's how the decision was actually made. So, in generative AI, the explanation can be as synthetic as the answer itself. Now, in the current state with LLMs, we are just beginning to understand what's inside the model at a high level. For example, through mechanistic interpretability work that identifies internal representations or directions. I link below the interesting work Representation Engineering, a top down AI approach to AI transparency, which seeks a better understanding on a whole range of safety relevant problems, including honesty, harmlessness, power seeking, and more, demonstrating the promise of top down transparency research. Now, these are model level explanations. We are still very far from being able to explain why a model answered a specific question the way it did. The equivalent of patient level risk factors, a faithful explanation for a single decision. I don't think it's reliably possible today. And while the chain of thought can improve model performance, it cannot be relied on as a true explanation of the model's internal reasoning, as we saw. Now, language models have unprecedented complexity. The latest constitution for the AI model Claude, published by Anthropic, talks of Claude's well-being and psychological stability, and includes statements like Claude's moral status is deeply uncertain, and Claude may have some functional version of emotions or feelings. So the concept of explainable AI for models this complex is a whole new ballgame. So the takeaways from this survey of explainable AI today, there are many techniques like Shapley values, Lime, and more to look under the hood and to understand the reasoning behind model predictions. We talked about the many motivations for XAI, from bias and fairness to trust and regulatory compliance, accountability, model improvement, and so on. And finally, in the LLM world, transparency and explainability is a fascinating, active research area. So, tomorrow we have an unconventional topic: why is for you. So, we'll explore what is the role of the individual as AI permeates every corner of our world, and also discuss the views of some leading AI researchers. See you then, and that's it for today. Bye.